All right, I think we're ready to get started. So before we get started, I just want to warn you that I have been feeling a bit under the weather the last few days. So if I fall off the stage, I want you all to just remember to go slowly outside, put a green thing in the box, and just forget you was ever here. All right? Deal? Great. So we're here to talk about asynchronous programming from the ground up in PHP. Sounds good? Yay! No, it's .NET, I promise. So before we get started, I'm Filip Ekberg. I used to live in Sydney, but now I'm back in Sweden. I don't miss the slow internet here, but I do miss the awesome weather. And it's true that in Sweden we do have a lot of polar bears roaming the streets, just as we have drop bears in Sydney. All right, so what I want you to do is that bring your cameras up, take a photo of me doing this talk, ping me on Twitter, and I'll send you a free copy of my book. Sounds good? The digital version. You have to buy the one in paper. All right, let's get started. So asynchronous programming. Is everyone in here a .NET developer? Excellent. So I imagine that for the last few years, you've all probably done a ton of asynchronous programming. You've been using the async and await keywords. You've done the TPL, using tasks, the parallel extensions, and all that. But a lot of the times, we feel like things just fall apart. You feel like the firefighter. You just add a lot of these keywords, and the application might work for most of the times. It does work really well. But then you run into these problems where the app deadlocks. And if you've never experienced a deadlock, it's probably because you've left the project before it even ran. Right? So asynchronous programming is really hard. The idea here is that we want to build applications that perform really well. So I'll take you through what we want to use asynchronous programming for, how we apply that in .NET applications, and how we can understand the state machine and everything that goes into these applications. So hopefully, when you go out of here, you've learned how to avoid deadlocks. But why bother doing asynchronous programming at all? What's the reason for us wanting to introduce this in our applications? Like the main reason when we first started doing this was to avoid unreliable apps. An unreliable application can be like a website that loads forever. It could be, in this case here, it's a mobile app that's telling us that, well, this application is not responding. The problem here might not be that the app actually crashed. It could be that the OS thinks that, well, your application is doing a lot of work in the wrong place, so therefore I'm going to tell the user to kill it. Right? So we want to avoid this here. And we've got patterns and principles to allow us to build better apps using async and await and a lot of other cool things in the .NET framework that allows us to avoid this here. So ultimately, we're here to improve the user experience. And the way that we do that is by introducing async and await and doing that properly. And of course, you probably want UX person fixing the UX for you. But we are developers, and we want to focus on building fast apps that are reliable. So the way that we do that is by leveraging all the resources available to us in our applications. So in this case here, I'm on my workstation at home. I got 8 cores, I got 32 gigs of RAM, and I got a ton of hard drives. So leveraging all resources means I want to be able to use my disks, I want to be able to use my memory, I want to be able to use all the cores. But those are all different paradigms. So when we talk about leveraging the resources, we talk about CPU and I/O. And we work with these two different things separately. So if we want to work with CPU-bound operations, we work with parallel programming. We take a problem, we divide that into equally small pieces, and we solve that on each core. And we've got parallel extensions to help us do this. So that allows us to just say, take this problem, solve it for me, divide that across all our different cores, and it'll figure out how many threads to start. It'll just let us solve our problems for us, which is great. And then we've got I/O. So I/O is a little bit different. We might have an application where we want to say, well, load this large file into memory. When it's available in memory, I want to be able to consume that file in my application. So what happens is that we introduce asynchronous programming, which allows us to say, for instance, when this thing here is done, notify me so I can work with that result. So those two are really fundamentally different. The parallel programming allows us to just solve a problem as quickly as possible, while asynchronous programming allows us to offload some work somewhere and be notified when we are ready to handle the result. So when we work with parallel programming, we could be using the parallel extensions. We could be saying that, in this case here, I want you to iterate from 0 to 100 and do that with all the available cores. So that's great, but we're here to talk about asynchronous programming. So how about we have a phone, for instance. My phone here probably got more cores than my first computer. I've got the latest Samsung Galaxy S8. It's like a hexa-core machine. It's really powerful. So if I run Xamarin and .NET on this thing here, I want to be able to leverage all the available RAM. I want to be able to use all my cores. And if I take the same .NET library and run that across ASP.NET, or if I run that on my workstation at home, I want that to leverage all the different types of architectures that I might be running the code on. So in this case here, we have these parallel extensions. And I want to combine that with asynchronous principles. And the asynchronous principles allows us to say, start this work and tell me when it's done. So we can combine these two different paradigms rather easily. So one of the times you might see this being used here is, in this case, we have a mobile application. We're simply saying, I want you to start off this asynchronous operation. And this asynchronous operation might have something parallel that it's executing itself. So we are starting this thing here. It's using parallel extensions in that asynchronous operation. It's easier if you look at the code, right? So in this case here, I'm simply saying, well, start off an asynchronous operation. Task.run here is in the TPL. It allows us to start off an asynchronous operation, and then we can subscribe to notifications when that's done. And inside this asynchronous operation, we are running this parallel.for loop. What's interesting about parallel.for is that it'll actually lock up the application unless you're doing this, because it's leveraging all the available resources, which means that it's also going to make use of your UI thread, which makes sense. So when we talk about asynchronous programming and making an application more asynchronous, we're talking about going from an application that's synchronous to asynchronous. That kind of makes sense, right? But we can also look at this as we're going from an application that's blocking code to a non-blocking application. So in our first example with the mobile app, it told us that the application is crashing. But actually what's happening in the mobile app is that we're blocking the working thread of the application. So there's one main thread running most applications. We have the UI thread for WinForms, WPF, Xamarin apps. There's one thread in ASP.NET application that's handling our request. If we're blocking that, it means that we're going to have a really bad experience for whatever is using that thread, right? So what we want to do is that we want to go from blocking to non-blocking. And the way that we do that is by avoid heavy lifting on our UI thread. Kind of makes sense. And in this case here, all we can do is that we can introduce this task.run, and something just runs somewhere else. All right? But we're going to try and understand why we get deadlocks. I'm saying here that we should never block our asynchronous operations. And I'll try and reiterate this a few times. Blocking an asynchronous operation means that we're saying, I want to wait until this thing is done. So just imagine for a while that you are the main thread. You're delegating all the work and looking over your asynchronous operations, and then all of a sudden you just blindfold yourself, and you have no longer any idea of what's going on. You can no longer keep track of your asynchronous operations. So blocking an asynchronous operation means that we can no longer look over our asynchronous operations. There's no way for us to know if they're going to be done, which results in a deadlock. And we'll look at some code later on, and once we look at the state machine and what's happening internally when we apply async and await, you'll get a better understanding of why this is a problem. So ideally, we want to take this application, the application that's giving the user a pretty bad experience, that's blocking the UI, and introduce a loading indicator that's also blocking the UI. But what's interesting here is even though these two things are clearly doing the same thing, they're no longer allowing the user to do any input, the user is more inclined to actually close the app in the first one, because the user doesn't know about the internals, right? They're more lenient towards just waiting for a little while longer if it's loading, especially if they've done a lot of work in the app. So we want to avoid having the user close our apps, even if in some cases it actually deadlocked. And to do that, we introduced the task parallel library. So the task parallel library allows us to simplify working with concurrent and asynchronous code. So concurrent code, that's parallel programming. And asynchronous code is just a way for us to run something concurrently and then get notified when that work is done. So if we look at this TPL, we saw a little hint of that before, and most of you have probably worked with tasks. So this task here allows us to start off some asynchronous operation. Imagine that we have a lot of work that needs to be done, and we simply want to be notified when that's done. So the most simple way for us to start this work is by saying task.run, do some work somewhere else. So you simply pass a delegate to this here, and it just executes that somewhere else. In some cases, though, we want to return some data from this as well. That's where we introduce the generic version of the task, and we're allowed to retrieve values back from this. Now, when we want to subscribe for what result we get from here, we introduce something called the continuation. So this is where it starts to get a little bit more interesting, because most of us have probably seen this and think, well, I already know all this, but when it comes to the continuations, that's where it becomes a little bit more interesting. So we can subscribe to when this is done here by introducing a continuation by saying, well, I want you to continue with this block of code when you're done. Now, when does this run here? So does this run if there's an exception in the task? Does this run if someone canceled the task? Or does it only run when there's actually a value that we can use? The continuation runs in all different scenarios. So if you cancel the task, if it's faulted, if it's completed, it runs all of those different scenarios. So when you're inside the continuation here, you probably want to check if it's actually completed. Right? So a lot of cases I see that, well, we're inside the continuation, so everything probably worked. But that's not necessarily the case. So in this case here, I'm just referring to the task outside of the scope to check if it's completed, but we can also get that task passed into this delegate. So what's interesting here is that we can work with this here, and we can check if the task is completed. If there's a result available, you get that by doing t.result or task.result. But you should only use task.result once you're inside the continuation. And I'll show you why in another moment. But just to take a look at this in another scenario, so imagine we have this WPF application. I'll be showing a lot of demos in WPF, but the same things applies to ASP.NET, mostly console applications, Xamarin, WPF, WinForms, and all the different types of .NET apps that you're working with. So in this case here, we have a WPF application. In the constructor, I'm simply saying, well, I want you to simulate 1 millisecond of work. So what we're doing here is that I'm simply doing a task delay for 1 millisecond. Now, what happens when the user clicks the button? In this case here, the task is clearly completed. But I'm telling this here that I want to subscribe for the continuation after it's actually completed. So will this here execute? How many of you think that this code here will execute? Excellent. So let's look at the code behind this here. So it doesn't matter if you can't read everything in here. So this is from the reference source. You can go into reference-source.microsoft.com, and you can drill into the .NET framework, and there's comments for everything for the entire .NET framework. It's really handy. So what we can see here is that at the bottom here, it's saying, well, if the continuation was not previously queued, we'll just execute the continuation. Right? So if everyone in here now expected that the code would actually not execute, you'd all have a bug in your app. Right? So let's look at a bit of tasks. Let's look at how we can work with this here. So I'll jump into Visual Studio 2017. Is everyone in here using the latest version of Visual Studio? If you're not, I can highly recommend it, because it's got a lot of features when you're looking over your tasks, especially if you work with asynchronous programming. You can see all the different tasks that are currently running. You can see threads that's being allocated, and you can see if there's any problems in those tasks as well. So the idea here is that I have a WPF application. I've simply set up a task here. I'm doing task.run, and in this task.run here, I'm simply doing thread.sleep. Now, thread.sleep just sleeps the thread that it's currently running on, which indicates that task.run is running in a different context. And then after that, we're simply returning hello world. So let's just run this app here, and just make sure that we set the right one as the startup project. We're going to look at a bit of ASP.NET later on as well, because there's some really interesting cases when working with asynchronous programming in ASP.NET. So I'll click run here, and after 2 seconds, we can see here that it says hello world. And if I click this again here, you'll see here that I can move around my window while that is actually, you saw that I couldn't run the, move around the window here because we have t.result here at the bottom. So the problem here is that I'm simply saying thread.sleep, and I'm clearly sleeping on a different thread. So what happens here is that we start off an asynchronous operation. That asynchronous operation tells it to sleep in that context. So it locks up the thread that it's currently running on. But then what I'm doing here at the bottom is that I'm blocking my code from continuing. Because what's happening here is that I'm saying, well, give me the result of the task. And when is the task available? Well, it's available after 2 seconds. So it'll block our application here. And if we do this for a longer time, like 20 seconds, maybe 30 seconds, Windows will think that the application crashed. And it'll tell us, well, you should probably terminate the app. On mobile apps, that window of when the OS thinks the application should no longer be executing, it's much smaller. So if you work with Xamarin, you'll notice that if you don't do this properly, if you do t.result or t.wait, you'll have a much worse experience with the app. So how do we solve this? Well, one thing that we can do is that we can introduce the continuation that I talked about. So I can say, well, when this task is done, I want to continue with something else. And in here, we want to do exactly the same thing. So we can skip that task for now. What happens if I just paste this code in here and run the app? So clearly, what I'm saying here is that, well, after 2 seconds, I simply want to set the result text to whatever gets back from that task. So if I click run here and move the window around, it doesn't lock up anymore, which is great, but I'm not getting anything in here. So the problem here is that the continuation, just as our task, runs in a different context. So it runs on a different thread, which means that we cannot change the UI from a different thread. That's basic UI programming. So if you have 2 threads, one is the UI thread and one is some other thread, you can't cross-communicate when it comes to the UI. So the way that we need to solve this is to use a dispatcher to invoke the UI and change the UI from that. But what's interesting here is that we didn't get an exception because the task actually swallows any exceptions. And we don't validate our tasks in here. So how do we validate the task? One way to do it would be to do .result. But we can't do that here because we're not returning anything, and we should never do .result because that blocks the app. So the way that we can do this is that we can introduce another continuation to check if this one worked. So we can say, well, when the continuation is done, which is also an asynchronous operation, sort of, we can say, well, I want you to continue with this block here. And this is where it becomes a little bit nasty working with TPL and the way that we did asynchronous programming prior to async and await. So now I can in here say, well, if T2 is completed or is faulted, well, how about you just tell me that and you give me the exception? Let's set a breakpoint in here. And if I run this with the debugger and click the button, it'll tell me earlier because I have the debugger attached. But I'll just jump through that, and we'll see that we get into this second continuation. Actually, we'll set this here as well. I'll click the button, run here. We can see here that after 2 seconds, we try to update the UI, and that fails. So it's going to tell us that, well, you tried to do a cross-threading call, so that's not going to work. But what actually happens is that we get into the second continuation, because when we try to change the UI, it throws an exception, it sets the task to a completed state or a faulted state, and we get down here and see, well, this task here is faulted. And we can see information about what's actually going on. Let me zoom in here. And we can get the exceptions in here as well and see that, well, you try to change the thread from a different one, right? So no one wants to do this. It's like if you're working with JavaScript and promises, it just becomes really nasty after a while. Because what you need to do now is, well, you need to check if this one faulted, right? So you say, well, let's continue with this one as well. It just becomes really nasty. So we don't want to do that. But this just shows you that, well, working with the continuation in this sense here isn't really going to work out for larger apps. It's going to be a bit terrible to work with in the long run. But if we just make this work what happens is that, well, we need to use the dispatcher. And in ASP.NET, that's called a synchronization context. So you can do this in WPF, in WinForms, in ASP.NET applications. The way that you communicate with the original thread is just a little bit different. In WPF, it's the dispatcher. In ASP.NET, it's called the synchronization context. So we can say, well, I want to invoke the main context. So we'll just do that. And once this is running back on the UI thread, there should be no problems updating the UI. And the UI no longer locks up. So we can move this around here really nicely, and after 2 seconds, it says hello world. So we kind of made the app a little bit better, but we also introduce complexity, which makes it easier for us to get an application that's going to be crashing. So not so good. But this kind of shows you that, well, asynchronous programming is really good, but doing it with just a TPL is problematic, especially if we have all these different fault states that we need to track and just need to make sure that we can access the data properly. All right, so let's jump into this here. So we saw that tasks are really good, allows us to easily offload work somewhere else and get notified when that's done. So we got into the continuation and saw that, well, there's some data available here, or there was an exception. We can check if it's canceled, if it's faulted, if it's completed, and so forth. So this is where I like to introduce async and await. Async and await is just really 2 contextual keywords. That pretty much means that all they're doing is that they're taking a lot of complexity and hide that somewhere else. It generates a ton of code to keep track of where you are in the state machine. It builds up the state machine and just does a lot of things for you. Okay? But there's no reason for it to change the runtime, which is what the contextual keywords are for. So you don't have to rely on a new .NET framework or a .NET runtime, sorry. So that's pretty good. So they just need to update the compilers to make sure that this works and compiles down to the same IL that can be executed by the current state machine, or the current runtime. All right, so async and await, they pretty much just allows us to hide complexity, which is great. Hiding complexity often means that we increase readability. That means that not only does our applications maybe become better for our end users, but also it becomes better for the developer. At least that's what we all aim for. But the problem here is that it does become a little bit more error prone. So this means that, well, we are introducing async and await. We know that working with TPL can be a little bit hard and problematic. And now we're just going to add even more things to make it even more confusing. So in this case here, we have a simple method. The idea here is that we want to run this method asynchronously. So the first thing that we do is mark it with the keyword async. Now, one of the misconceptions is that this just automatically makes everything inside it asynchronous. That's not really the case. So marking something with async only prepares for asynchronous operations. It's when we introduce the await keyword where it becomes a little bit more interesting and where it actually introduces all these asynchronous principles. So we'll look at what happens when we actually add that keyword, both of the keywords, and what's generated. But just remember that when you add the async keyword, you only prepare for using async or asynchronous operations. And when you add the await keyword, that's where you introduce your continuations. And that's where you start doing your asynchronous code. So basically what that means is that, you see, the var x is equal to 10. That's not going to be executed somewhere else. It's going to be executed on the caller thread. So as I said, the await keyword is where pretty much all the magic happens. The await keyword marks the continuation. So instead of doing the continue with thing that we saw earlier, we can simply add the await keyword, which makes it a lot easier to read. And what's even better is that it also validates that the task that we're awaiting is completed successfully. That means that it's checking if there's any exceptions or if there's any problems, if it was canceled. If it is canceled or if there's a problem, it'll just throw that back to the caller. And then it's up to the caller to make sure that it handles that properly. So that means that when we mark something with await, we don't want to run the code after it until it's done. So what happens is that when you see the await keyword, it returns back to whoever called the method with a reference to that ongoing work. So that's really confusing, really. So Let's look at an example. In this case here, we have a button click. The first thing that we're doing is that we're calling a method called runAsync. So it's going to go down into runAsync. The first thing in runAsync is doing runInternalAsync. And then inside runInternalAsync, it does a task.delay. So this is the first time it doesn't really call anywhere else. And we don't really care about what's happening internally in task.delay. But what it's doing here is that it's simulating 100 millisecond work. So when it sees the await keyword, it's going to return back to the line, or the code that executed that code. So that'll be await runInternalAsync, and that in its turn sees the await keyword, which returns up to the button click handler. So now we're at the top of the chain. What happens now is that it's just keeping track of all the work that's going on. So the await keyword here and the async keyword set up state machines, and they're making sure that it's jumping to the correct context and that you're on the correct thread. So after 100 milliseconds, we're going to come down to hello world here. And after hello world is going to be returned, actually what happens when you see the return keyword is that it takes whatever you want to return, the result of that, and sets that as a result on the task. So what happens is that, well, we saw the await keyword up here, which means that we grab the result. Not only does it validate that there was no exceptions or cancellations, it also grabs the result of that asynchronous operation. All right, so it takes that hello world, and we return hello world dash from runInternalAsync. And then that returns up to our button click event handler. Right? So a lot of steps just to make something a little bit smoother for the end user. But there's a lot of things that can go wrong here. And if I wrote this in production, I would do a lot of different things as well. Let's look at a different example. So pretty much the same code, but I've left out the await keyword here at the top. So what we're actually doing now is that we're calling runAsync without the await keyword in front of it. Because actually what happens is that it first calls the method, and then it gets a task, and then it awaits it. But in this case here, we don't see the await keyword, so it still calls down to runAsync, which calls runInternalAsync, which awaits the task.delay. And that means that it's going to be returning up to the next line that's in queue to be executed. And since this has not completed yet, so 100 milliseconds is not up, it's going to run the next line after runAsync, because there's no await keyword. Now, if we introduce the await keyword, it's going to check, well, is the task completed? Right? So we got the runAsync task that we're keeping track of the work inside runAsync, inside runInternalAsync, which in its turn is keeping track of the task.delay. So when we introduce the await keyword here, it sees that, well, this completed now, so we can return hello world, which returns inside runAsync, and then we can get the result in here. Right? Just to make this even more confusing, all of these different ones are running on the same context, which means that we call this from the UI thread. So whenever we see the await keyword, whatever's after that is going to be running in the same context as the code before it. All right? And just to make that even more confusing, it's not true for ASP.NET if you use configure await false. But we'll try that on later on. Does this make sense? Good. Or just blowed your mind and you're just all sleeping. All right. So what's the difference between doing await versus like task.continue with? Besides the obvious things that, well, you know, it looks better, it also makes sure that we execute the code after the continuation on the same context. So with the continue with here, we actually run the continuation on a different context. Doesn't necessarily mean that we're on the same thread that we did our asynchronous operation on, and it doesn't mean that we're on the UI thread. We're somewhere else. Right? So we have to worry about the cross-threading ourselves and all that. But when we come down to just normal continuation with the await keyword, we're at the original context. And what also is really good with this is that, you know, it validated the task, which means that we don't, like, it throws the exceptions if there's a problem, which is essentially what we really want. So the really bad parts about async and await is that, you know, it increases complexity. And you can't really see the complexity, but it really does make your code, if you decompile that, a lot more complex. And even if it seems like, well, I can just add the async keyword, and whenever there's a task, I'll just add await. Well, it's hard to master. It's funny, because I've done a ton of workshops and talks on asynchronous programming, and I learn something every time, and I still do deadlocks, and I still do crappy applications. I don't know if I'm still like a slow learner, but it's hard to master. Let's just leave it at that. And if you've never had a deadlock, I promise that you'll experience a deadlock sooner or later. It's really easy, especially when it comes to async and await, because it becomes harder to, separate what's running somewhere else and what's running on the same context, which is essentially where you seem to run into deadlocks. It's when you forget which context you're currently running on. Normally, when you get a deadlock, it's because you're saying, well, run this thing here, and I'm going to block until it's done. Normally, you don't want to block. You just want to wait for the work to be done. But sometimes it's hard to know where you're running the code, and we'll look at that soon as well. But before we do that, we need to understand what the state machine is all about. The state machine allows us to keep track of all our work. So whenever we add the async keyword, it introduces one of these state machines. And I tend to say, like, compare the state machine to a child that's sitting in the backseat of your car just asking over and over again, are we there yet? Is this annoying little kid just asking you all the time if we're there? That's pretty much a state machine. It's just keeping track of all the work. And when it knows where to go, it jumps to the correct context on the correct thread, which is essentially what we want to do. It keeps track of the state. Makes sense. But what it's also doing is that it keeps track and handles all the results, and potential errors. So that means that if we're throwing an exception inside our task.run, it'll capture that, which is really good. And it also makes sure that it can execute the code after we have the await keyword. So it goes into the continuation, and it runs that in the correct context. So what does applying the async keyword really do? Well, it introduces this state machine. And introducing a state machine means that it's doing a lot of work. It's generating a lot of code. And this code is essentially, it's going to take our method body and move that into somewhere else. It's not only going to create a new file, it's going to tear everything apart, move lines all over the place, and as soon as you have the await keyword, it's just going to make it even more complex. So just looking at this very small example here, we're adding the async keyword. You can see that we have the debug.write line at the bottom. So when we compile this here, well, you would probably expect that it'll look a little bit similar to this here. How many of you have looked at decompiled async code before? OK, good. So you all know what it's going to look like, pretty much. So what happens is that it introduces like nothing that looks like our code. It took the entire method body, moved that into something called run async d__1, which is the generated state machine. And inside the state machine, it keeps track of the asynchronous operations. It keeps track if there's any errors and any results and so forth. Now we can see here at the bottom, so keep this in mind. This is really interesting. So we have this, it returns a reference to the ongoing work. That means that when we call an asynchronous operation, or a method that's marked as async and it returns a task, we can check if it's faulted. We can check if there was an exception, if there's a result available. That's really good. That's helpful. So keep that in mind. So if we take one step further, when we look inside the state machine, we'll see here that, well, we do have the task.delay for 2 seconds here, which is the same code that we had earlier. And on the line above it, it introduces this variable, which is our var x is equal to 10. And then what it's doing is that it's checking if it's completed. And then at the bottom, when everything is done and it's in the context of running this, the continuation of the code, we can see that we have our debug.write line. That's good. So this is pretty much our code that we had here. Now, what's really interesting here is that this is all running on the same thread that you're calling the method on. So if we just step back a little bit here, we have run async here, right? So if we go back one step further, if you call this method here, what I told you earlier is that this doesn't just magically become asynchronous. It generates a state machine, and we can see here that it's running our state machine. On the line above this here, it's doing builder.start, which is starting and running all the code inside the state machine. So all of this code here is, in fact, running on our UI thread, if we're running this in WPF. All right? So keep that in mind when we're looking at deadlocks, because this is where a lot of people seem to be deadlocking, at least once or twice. Third time, well, you probably shouldn't be a developer. I'm joking. All right, so this is where we talk about async void. Does anyone know when to use async void? Or never? That's the right answer. I didn't hear anyone say it, but let's just imagine. Async void should never be used, except in one case, and I'll show you that soon. So async void is pretty much like, it's the hottest summer day, especially in Sydney. You go to the beach, you stand in line for 40 minutes to get your ice cream, and as soon as they hand you the ice cream and you walk out of the line, you just drop it. Like you just want to lie down and cry, right? If the sun doesn't kill you, the sharks will. That's async void for you. So is it really that bad? Well, let me just show you a little bit of code here. So what happens here? It's the same code that we had earlier, but I've removed async task. It's doing async void instead. So if we look at the decompiled code of this here, with the compiled code, we can see here that it's doing exactly the same thing that we had earlier, except that we're now using this async void method builder, which handles exceptions and problems a little bit different. If there's an exception inside this state machine here, it'll just tear down the entire application. That sounds good, right? Why is it doing that, though? Well, it's because, as we see here, there's no return builder.task at the bottom. We no longer have a reference to the ongoing work. So the only way for the application to tell us that there was a problem is to just kill the app. Then you'll certainly know there was a problem, and we have to fix it. So, I don't know if anyone else in here heard that Elon Musk said that I think that AIs are going to destroy humanity and all of that, right? Everyone heard that? Well, I think async void is going to kill us all, especially if we do it in cars. All joking aside, how do we fix this? It's really easy to fix. The way that we fix this is by just don't do async void. We change this to async task. But what do we have to do if we mark this as async task? So I said earlier that the await keyword is validating that the tasks are all done properly. And what we have to do here is that we have to make sure that all the code in this part here executed properly. It's better that the app no longer crashes, but we also want to make sure that there's not any problems in the code. So the way that we check that this is, in fact, working is by introducing the await keyword. So if we look at a button event handler, can we mark that as async void? Well, we can't mark this click event handler as async task, right? Because that would break the delegate. So this here needs to be void. So if we simply do this here, I'll just show you this example here. If we have await task.delay, delay 2 seconds, we have to mark this as async. So I told you to never do async void, but there's not really any options in here, right? So I can't mark this as async task, and pretty much all the initialization of asynchronous programming is through event handlers when a user clicks a button or something happens, right? So we need to be able to do this. And the only way that it's not going to tear down the application is by making sure that there's no exceptions in here. So how do we make sure that there's no exceptions in here? Well, we don't write bad code. Super simple. Now, what we do is that we wrap all our code in a try-catch block. Got to catch them all. We do this. Now, we want to write as little code as possible inside our try-catch block. That's what we've all learned before, right? So we want to make sure that we don't have too much code in here that could potentially fail. So what I normally do is that I try to have very small async void methods when they click event handlers. And then I call out somewhere else. In this case here, I'm simply just validating that our code worked properly. So now, this won't tear down the application, but I probably have to make sure that there's no problem in the catch block, right? So we might want to clean up the resources. If there's a problem, we can clean that up in here. And if everything in the application is async, and we might want to log this to a database, if you do stuff in here as well, that's asynchronous, because now you can use await inside catch blocks and finally blocks as well just make sure you have one more layer of try and catch so it doesn't tear down the app. Right? So this is just an example of if you would have like a database call here, like log to DB, or clean up, or do something like that. So it's really handy. So in this case here, when we run this here and when we have this code compiled, it's allowing us to work really easily with all this asynchronous code, right? It's more beautiful than doing all that task.run business that we saw earlier. Even if task.run is the way that we initialize our asynchronous operations, we want to avoid doing the continue with on those tasks because this is a much better approach because it takes care of looking over if there's any fault. It gives you the result. It just makes it a lot easier. But as we saw earlier, there is one use case for using the continue with on tasks. It's, for instance, when we start a task somewhere else and we always want to run something when it's done. Then we might want to just do .continue with. Because what happens when we introduce the async and await keyword is that it introduces all this complexity, right? In this case here, it might not make any sense for me to introduce a state machine to move this entire block of code into that state machine, right? Doesn't really make any sense. So as we saw earlier, if we have this private async, let's say string, run async, ideally, we can, in this case here, for instance, say await task.delay. Let's do 1 second. Hello world. So what we're doing here is that we're simply introducing an asynchronous operation, and this needs to be task of string. If I can work out this keyboard. Been on a Mac doing Xamarin for too long, so you forget a normal keyboard. All right, so what we want to do now is that we want to grab that hello world out of this here. And what we saw earlier is that, well, if we call run async, this returns a task, right? So just as we had earlier, we can say, well, give me the task of run async. Now what happens here is that it goes into run async, it runs the task.delay, and then after that, we get the result. So it takes that result, hello world, which we have here, it sets that on our T here. So we could say, well, I want you to give me the result by doing t.result. This here will, in fact, give us hello world after 1 second. But this here would block the application. And it would most likely deadlock as well. So I want you to think about that for a second, why this would deadlock. And I'll get back to that in just a little moment. So the way that we get the result out of that without any hassle is to say, well, give me the result. Is equal to, result is equal to await t. So that's pretty easy. And this here validates that there's no exceptions. It checks if there's any exceptions. If there's an exception in t here, it's going to take the exception and set that as a full state on this one. And if it sees that, it's going to throw it back to the caller. So the await keyword will make sure that we can grab that exception and we can get that Pokemon in here. Super simple. Now, a lot of people ask me, well, what if I have an asynchronous operation that returns something asynchronous, such as the HTTP client? You can actually, what we can do then is that let's say that we get hello world from a stream from somewhere. We might be doing it from a file. So we can do task.fromResult, which is a good way for us to fake that this is running as a task. And we have a task of a string. And then we can have await t here, which returns a task of string. And then we can have one more await. And sometimes there's even more tasks. But yeah, you get the point. So we can just chain all these awaits together. So it might not become readable, but you can do it. So a task can return a task, which might be an asynchronous operation like an HTTP call. And then you need to read the content from the HTTP request, which is another asynchronous operation. So then you can chain up all these awaits like that. All right. And if we compile this here, and I'll just close off the app, and we head into Reflector, I'm just going to refresh this here. We'll see if it's all good, compiled. So we see here that we have the button click event handler, which is introducing this state machine. It's introducing the state machine that keeps track of run async and the result of that. So we can drill into that. And this is a void method, so it's doing the async void method builder. But if we go into the state machine, we have a method called moveNext, which is running all our code. And this here is all the code that's executing and keeping track of everything that we have inside our button click event handler. Wow, it's a lot of code. For just this little part here, right? So it's try catch. We're running just a method, and we're doing a wait, right? So we have, what, 70 lines of code in here to do that really simple thing. So one thing that I tend to talk about is how we can be more efficient when we work with asynchronous programming. And one of the things that we want to avoid is, of course, deadlocks, right? So deadlocks is pretty easy to avoid. An example of getting a deadlock, in this case here, this example looks difficult to understand, but it's really not. So we're introducing a 1 second delay. I continue after that, one millisecond, sorry, and say, well, after 1 millisecond, I want you to run something on the UI. And then at the bottom here, I say, well, I'm going to lock up the UI until you're done. So how do they know that it's done, right? How does it communicate back to the UI to say, well, I'm done? Yeah. If we do this, it just blows up, which is not so good. An easier way for us to get a deadlock is to simply block our state machine. So I said earlier that, well, if we do runAsync.result or runAsync.wait, the state machine that's keeping track of all the asynchronous operations, it's running on our calling context. So that means if we introduce this code here and do a wait, or we're blocking this here, we're going to blow up the app. It's not going to blow up at all. It's just going to not stop responding because it's locking up. So always avoid doing .wait. The only time you do wait or .result is if you work with a console application where there's no UI thread. You can even deadlock ASP.NET. So yeah, just avoid this. Another thing that I see a lot is like unnecessary state machines. So what do I mean by that? Well, in this case here, we have a method called runAsync. RunAsync is in its turn calling runInternalAsync, which is marked as async task. It's awaiting something, it's calling something async, and then it's calling something internal async. What happens here is that each of these methods are going to introduce their own state machine, which is going to keep track of the work inside that state machine. And each await keyword is going to be working with a continuation to make sure that it's jumping to the correct context. Each await keyword is going to make sure that there's no exceptions, and it's going to check the result and so forth. That's a lot of work just to do one simple thing. What do we want to do here? Really, whenever we want to use the await keyword, is when we want to get a result after the execution. So if there's nothing after the continuation, we don't really need to await. So the way that we clean this up is by simply remove async and await from the method that simply return back to the caller. So in some cases, look at the method chain here. So at the bottom, we're returning task.delay instead of marking it as async task and doing await. It's simply doing the same thing. So when we looked at the builder earlier, when it compiled the code into the state machine, we saw that the method signature changed to just builder.task, which returns a reference to the ongoing work. But the reference in this case to the ongoing work is just simply task.delay. So we can return that up to the top level, or whoever wants to work with it, and then has something after in the continuation. So the first time that we need to introduce a continuation in this case is when we do runAsync. Does that make sense? Right. So another thing that I want to talk about is cancellations. So cancellations is a really interesting topic. Is anyone in here doing mobile? Xamarin? No one? Oh, just a few of you? Yeah, so one of the things that I've been doing a lot is optimizing when user inputs data, for instance. I want to make sure that, well, if they still write something and I'm going to search for something online, well, I just wait until they've finished writing, and I can do that with smart cancellations or tricking it using tasks, which is pretty interesting. You can probably do the same thing if you're working with WPF or ASP.NET as well. So just an example here. This is more like a CPU-intensive thing, and it's not the best example, but it'll give you an idea of the problem that we have here. So I want to be able to cancel this operation here. So this is a long-running operation. There's a little bit of mixture of talking to the UI, and there's some asynchronous code in here. So I want to make sure that I can use this in my app, and I want to be able to cancel this operation. So the way that I introduce this is by introducing something called a cancellation token source. So the cancellation token source allows me to get something called a cancellation token. Now the token is what's traveling throughout all our different asynchronous operations. And ideally, you pass that down along the line to the call at the bottom, and you can just track if it's been canceled along the way. Now, I can use this cancellation token source by simply saying cancellation token source.cancel. Can I see a show of hands how many of you think that this is going to cancel my operation? Exactly, it's doing nothing. Correct. So why is it doing nothing? Well, how would it know where to break my app? How would it know where to stop executing my code? So the way that we introduce the cancellations is by saying, well, just throw an exception if there's been a cancellation requested. So this here is really neat. And you can use this in a variety of different scenarios. So I've done this in mobile applications. I call it smart cancellations. So what I do is that I set up a task that's running for, let's say, 400 milliseconds. Each time the user presses a button, I cancel the task and just restart it. And if it has not been canceled, I go ahead and do the web call. Right? So that means that if there's nothing input for 400 milliseconds, I don't do any cancellations, and the user didn't. The user wants the data, right? All right, so how many of you are doing ASP.NET? Ooh, almost all of you. That's awesome. So everything that we've talked about up until now is applicable in ASP.NET. The only difference in ASP.NET, which makes this really hard, is the synchronization context. So the synchronization context is pretty much like our dispatcher.invoke. So imagine we get into our ASP.NET application, we got an action. That's running on one thread. Then we start doing asynchronous operations, and the way that we get back to the original thread is by doing synchronization context.current.post, for instance. This is what it's doing internally to get back to that original context. So how many of you in here, so all of you are pretty much doing ASP.NET, and how many of you have been told to always do configure await false? So a handful of you have been told that. So what's interesting here is that if we do just await task.delay here, so this is applicable in WPF as well, but this is an ASP.NET application. What happens here is that we're not forcing this line back to the calling context, which means that all the code after, inside our continuation, is behaving like we were doing this with .continue with. All right? But in this case here, we are executing the code on the original context. So why is that important, and why is that such a big difference? Well, the thread pool in ASP.NET is limited, which means that if it can just pick whichever thread you want, or whichever thread is available, that's going to be a lot faster. So doing configure await false is a lot of times faster, but it's going to run you into a few different problems. So let's look at a few of the interesting cases in ASP.NET that gives you a little bit of a headache. So I've got an example here. This is a web API. And I've got my values controller here. And I'm just going to run this here. And you'll see, run the right app. And you'll see here that what I'm doing is that I'm using something called the cache. So I'm using http://context.current.cache. I'm setting that to hello world. I'm calling an asynchronous operation that's doing something in the background, but I'm just waiting for that to finish before I return something back to the user. Super simple, right? So what happens now is that, well, it's going to go in here. It's going to set our cache and test here to hello world, and then it's going to return that back, and we can see that we have hello world here. Super simple. Now, what happens if I say, well, configure await and do false here? Can I see a show of hands? How many of you think it's going to be the exact same result? Okay, a couple. Great. I like that my questions aren't all that obvious. not too leading in my questions, it's actually going to show us nothing at all. The problem here is that what we're doing is that we are first setting a value in our dictionary to something, and this dictionary lives on our current thread that we are using when we are executing this for the user. So it lives in the context of the original thread that's spawning this user request. And what we're doing here is saying, well, I don't really care which thread you use to return back to the user. So that means that all the code at this part here is no longer running in the same context as this one up here. So 2 different threads, which means that it no longer has access to this thread static thing. So obviously, threads statics aren't really the best thing. Probably shouldn't use that. But it also means that, well, you couldn't use sessions. And everything from the user principal would probably not transfer over here either. Right? So that kind of changes it a little bit. So you need to think about that. But what makes this even more interesting is that configure await false is just context aware. So it's aware of its own context, which means that if we do this here, and this is interesting, if I introduce a new method called public async task run async, let's call it run async 1 just to make it more confusing. I'll just take this code here. I'll pop this down here at the bottom, and then I'll do await run async 1. Now, how many of you think that I'm going to see hello world? Half. All right. Let's see what actually happens. So what it's doing here is that it's context aware, which means that if I move configure await somewhere else, it's a different context. Which means that, I don't want to spoil it, we're going to see hello world here, right? So that means that, let's say that we are at thread 1 here. That means that we are at thread 1 here as well. But that also means that we are at thread 1 here, and this is returning from thread 2. Confused yet? So this is why it's really important to think about whenever we have a method that's using configure await false, just make sure that after you don't need anything from like the user principal or the context of the previous operations, especially if it's static variables, right? Everything else is the same in ASP.NET as we talked about earlier in WPF and WinForms and console apps and so forth. So one thing that you want to do is async all the way. And I'm just saying this because you shouldn't just break your async chain and have like an async void in the middle, because that's just going to make it really horrible. It's one way to like tear down the app and get a lot of unexpected exceptions. But just do async all the way. And if you don't have anything in your continuation, just return the task that's referencing that ongoing work instead of introducing async and await in that particular method. And remember that ASP.NET makes it easy for us to use async and await as well. But if we apply just configure await to everything, it's going to be hard, right? So if you want to sit down at your own time, I've got a Pluralsight course. And if you want a free trial for that, just hit me up on Twitter, and I'll figure that out as well. And remember, take a picture, ping me on Twitter, and I'll give you a free book. Nothing's ever free, so please put a green thing in the box there. I'm going to stand there and look at you, and if you didn't, you won't get the book. Just joking. So just to wrap this up, async and await is really good. It makes it easier for us to build asynchronous applications. And even if we go back to the basics, there's always something that makes us think about what's really going on under the hoods here. Now, hopefully, you'll have a better understanding of how not to get a deadlock and what's really happening when we introduce these keywords. So thank you so much. I'm Filip Ekberg. Please hit me up on Twitter if you have any questions.